Okay, so we're going to continue with respiration. And so today we're going to talk about how it's controlled. So what is the drive to breathe? When do you want to breathe faster? When can you breathe slower? And things like that. All right, so where is the primary source of control for breathing? Well, it's in the medulla and the pons. So if you think back to your brain, and I'll show you a picture, below the brain and the brain stem, there's an area called the pons and the medulla, and these are where your respiratory groups are. You have a dorsal respiratory group called the DRG and a ventral respiratory group. Now, the dorsal respiratory group is kind of an integrator. It takes information, input from stretch receptors and chemoreceptors, and it feeds that information to the ventral respiratory group. And then the ventral respiratory group sets your breathing rate, which is called eupnea, all right, which is about 12 to 15 breaths a minute. So kind of like the SA note of the heart. So it's going to set the rate that you breathe. And it has neurons that go to muscles. So it has inspiratory neurons that will excite the inspiratory muscles, and it does that via the phrenic and intercostal nerves. And there are expiratory neurons that inhibit the inspiratory neurons. They just stop them from being able to fire. Because remember, inspiration is active, expiration is generally passive. So just to get your visual on where this is, so again, here's your brain stem in the box. So in the pons and the medulla, so in the medulla you have your DRG and your VRG. So the DRG is here, and then the VRG is the ventral respiratory group. But you also have something called the pontine respiratory centers, which is up in the pons. And its job is to interact with those DRG and VRG in the medulla oblongata, and to kind of smooth it out, to kind of smooth the respiratory pattern, to keep it from being kind of spastic. I was trying to think about how I would think about this. And so if you remember the cerebellum, it kind of smooths your gait out. If you think about 201, we talked about you can walk without a cerebellum, but it'll be jerky. So the pontine respiratory center kind of smooths out and evens out your breathing rate. So again, the DRG is taking information in from receptors and going to integrate that information and carry it to the VRG. The VRG actually has the nerves that go out to the external intercostal muscles, tongue-tied, and the diaphragm, and those are your muscles of inspiration. Okay, so that's kind of the part of the nervous system that is needed for breathing. And this is all autonomic, okay? You don't have to think about it. This is why if someone is clinically brain dead, they don't have an EEG, their cerebral cortex is no longer working. As long as the brainstem is intact, a person can continue to breathe. And it's going to be able to do that because we're also taking in the chemistry of our body. So there are chemical factors that also help to promote the drive that we need to breathe. And we talked about this a little in a previous video about CO2. So CO2 is really the driving force for breathing in the normal circumstance. And so if CO2 levels rise in your blood, we call that hypercapnia. Okay, hypercapnia is increased CO2 levels that are accumulating in the brain. And so we know that CO2 levels, if you think back to that equation that we did, CO2 plus water will result in the formation of carbonic acid, which will then break apart and release hydrogen ions. And so we know if you have a lot of hydrogen ions, then that means you have a pH that's going down, becoming more acidic. And so that's going to be picked up by chemoreceptors in the brainstem, okay, in that DRG. So these chemoreceptors are going to then tell the respiratory regular centers, the VRG, that we need to breathe faster. Okay, and we need to breathe deeper, faster, and get rid of that CO2 so that we can drive the equation back that way, blow the CO2 out, and take the hydrogen with it in the form of water. So think about all of this integrated together. So your arterial CO2 levels are going up. So think holding your breath. So that CO2 is going to cause a increase in hydrogen ions, which is going to decrease your pH in the brain. That's going to cause the chemoreceptors in the brain to respond to those high hydrogen ions. You're also going to have peripheral chemoreceptors that are also going to be picking this up as well. They're going to send information to the medullary respiratory centers. They're going to increase their efferent impulses, their response out to the respiratory muscles, causing the muscles to contract harder and faster so that you breathe bigger and deeper, and you get rid of more CO2. You're increasing your ventilation. If you're blowing off CO2, you're blowing off water, you're getting rid of hydrogen ions, and your pH will go back to normal. Okay? So that is one way that breathing is controlled based on the amount of CO2 you have in your blood. Now, if you're hyperventilating, okay, so you're breathing too fast and too deep, and you're exceeding the need to get rid of CO2, you're blowing off too much CO2. You're blowing off too much CO2. Your CO2 levels in your body are dropping. We call that hypocapnia. And when that happens, you may get cerebral vasoconstriction. You may get ischemia. This is what you do when you start to hyperventilate and kind of feel dizzy and pass out. So what do they tell you to do? If you're hyperventilating, what will they tell you to do? Kind of put your head down, but blow in a bag. If you're blowing a bag, you're also breathing back in. You're breathing back in the CO2 and bringing it back into your body. So that's why you breathe into a bag, so you're not getting rid of so much CO2. You're actually bringing some back into your system so that you don't pass out. If you're not breathing at all, that's called apnea. And so if your CO2 levels are too low, you'll just quit breathing. All right, so too high of CO2 is a drive to breathe. Too low of a CO2 will cause you to quit breathing. What about oxygen? Does it make you breathe? I mean, we know we need oxygen, so we can have cellular respiration, so we can have ATP, but is it a driving force? It can be. It's not your main driving force, but obviously if oxygen levels get way out of whack, we have a secondary response system that goes, hey, we need to breathe. So we do have chemoreceptors in the aorta and the carotid arteries that can sense O2 levels. And so when they're excited, because your O2 levels are too low, so if you have low O2, that's going to cause those carotid body and aortic bodies to be excited, and they're going to cause your respiratory centers to speed up and breathe more, to bring in more oxygen. You're not going to see that unless your oxygen levels really, really drop. So it's got to be a pretty low drop. Normal oxygen levels are about 95 millimeters of mercury. If it drops to about 60, then your oxygen centers are going to kick in and make you breathe. And so just to show you where those are, again, your carotid bodies are here, your aortic bodies are here. They're tied into your brain and then out to your lungs. Just to make sure you remember aorta and carotid bodies. When I say that, you know what I'm talking about. All right, so other chemical factors. What can influence arterial pH? Okay, we know it can be modified by CO2. All right, so you can, if your pH is too high or too low, you can either speed up or slow down your breathing to either change the amount of CO2 in your blood and drive that hydrogen ion. Remember, if you blow off CO2, then you're going to be taking hydrogen with it. If you hold on to CO2, you're going to be pushing hydrogen back into your blood and lowering your blood pH. So if you have a low pH, if you look at your blood pH and the pH is low, it's acidic, it might be because you're holding on to CO2. Okay, you're not breathing, the CO2 staying in your body and the hydrogen ions are staying in your body and it's driving your pH down. But that's not the only pH changer in your body. There are other sources of acids in your body. One is lactic acid, which you get like after exercise, that burning in your muscles. So that could change your blood pH, and you might change your breathing rate to accommodate for that. Well, again, we're going to talk about acid base later on, so you'll see this again. Another source of acid is if you're diabetic, with diabetes mellitus. There's something called ketone bodies, and those are a result of breaking down proteins, because remember, diabetics can't use sugar, so they start to resort to other sources to make ATP. And so one of the things that they do are break down proteins, which give you ketone bodies and gives you something called ketoacidosis, which is going to change your blood pH, cause it to become more acidic. So if that happens, then you can adjust by your respiratory rate. So you will start to breathe deeper and faster to get rid of CO2 and to start driving that hydrogen out of your body and bringing that pH back up so that it won't be so acid. Okay, so it may not be CO2, it could be some other sources of acid. But regardless of what the source of acid is, your respiratory center will respond by blowing off more CO2 to try to get rid of that hydrogen. What other things can drive your breathing? You can have some irritants in your lungs. So you actually have receptors in your bronchioles. So if you breathe something in and you feel like you got a cough, there's going to be a reflexive constriction of those air passages because you don't want it to go further down into your lungs. So if something gets into your bronchioles, they'll actually spasm to prevent it from getting further down into your lungs and causing blockage. And then hopefully that will cause a response for you to cough or try to sneeze it out. So you try to get it out of your lungs. There's also an inflation reflex. This really is not so much about regulating how quick or how fast you breathe. It's really how large a breath you can take. And it's called the Hearing-Brewer reflex. And there are actually stretch receptors in the pleura and the airway that are stimulated when your lungs inflate, and once they get to a certain size, then they'll send inhibitory signals to the medulla of your brainstem and cause the inhalation to stop and allow you to exhale. And it's really more protective, so you don't overinflate and bust a lung. That's really what it's for. Okay, so you just can't take. There's a limit to how much air you can take in without, busting a lung. All right. You also have to adjust your breathing if you exercise. So you will adjust your breathing based on how hard you're exercising. So how hard and how long you're exercising, you'll adjust your breathing rate. And you know that if you go run a mile, you may be breathing a little bit hard. You run 2 miles, whoo, you're about to die. You're breathing so hard. This is called hyperpnea, which is when you're breathing faster than normal. And so you increase your ventilation anywhere from 10 to 20 times normal, and that's to account for your metabolic needs. Blow off more CO2 that you're building up in your body due to all that metabolic processes going on, and bring more oxygen into your body in order to make more ATP. But what you'll find is that even though you're breathing in, you're kind of breathing faster, the actual levels of your CO2 and oxygen in the actual tissues remains about the same. So you don't really see too much of a change in your CO2 levels and O2 levels and pH levels in your body based on that increased ventilation when you're exercising. All right. And some people, you'll even see if you're about to exercise, you'll already kind of start to change your breathing. So that's kind of something that you see with training. So the more you train, even the thought of exercise will cause your breathing to start to anticipate exercise and kind of get you ready for that increased exercise load. You also have to adjust your breathing based on altitude. So if you go to high altitude, you'll notice you probably are going to be breathing deeper and faster, really trying to catch your breath. You just cannot get enough air in. If you go too fast, if you fly into or go to altitude too fast, and when I say altitude, so sea level is at 0 feet, okay? And then we know Mount Everest goes all the way up to like, I will say 30,000 or just short of 30,000, somewhere around 30,000 feet. When you say at altitude, that's 8,000 feet. So anything at 8,000 feet or above is considered altitude. This is where you really start to see physiologic changes to your body when you start to go up. Now you'll see those if you start to go to 4, 5, 6, 7,000 feet, but true altitude is at 8,000 feet. And this is what they pressurize airplanes to. So you can get in an airplane and they immediately pressurize that thing to altitude, to 8,000 feet. So that's why a lot of people feel really bad on an airplane. And it can kind of give you a little bit of what they call mountain sickness. I always get a headache on an airplane because they've adjusted me to 8,000 feet so quickly. Because typically, if you were to drive to the mountain, it would take you several hours to get there. If you were climbing, it would take you several days and give your body a chance to acclimate. So people who fly from like Miami to Denver and fly into the mountains really quickly, they can get mountain sickness pretty quickly. They've been at 8,000 feet in the plane, they land in Denver, they go out to the mountains and go to 10,000 feet, and they have a headache, they get short of breath, nausea, dizziness, and that's pretty typical. If it's really bad, it can be lethal. You can get such mountain sickness that you get edema, cerebral edema, and pulmonary edema, and that can be fatal. So you'll see this in mountain climbers, maybe at Everest. They've gone too high, and they start to have see visions and spots and feel faint, and they're at risk of mountain sickness and possibly death. The only thing you can do is get down, just come down. But if you go slow and give yourself time and acclimatize, then your body will adjust to the altitude. And we talked about that earlier with erythropoietin. And so your respiratory rate, you'll learn that you're breathing a little bit deeper in the mountains. Every breath's a little bit bigger than it is down at sea level, so you're adjusting. And then finally your kidneys kick in. They send EPO out to the bone marrow. Your bone marrow makes more red blood cells. That way your red blood cells can bind more oxygen and increase your oxygen carrying capacity. So finally you acclimatize, but it can take 3 to 4 days to do that. All right, so all those things play a role in controlling how you breathe. All right, I'll see you in the next one.